Imagine a commercial airline that operates by flying a Boeing 747 across the Atlantic, landing it once, and then immediately pushing it into the ocean. No transportation business on Earth could survive with those economics. Yet for the first 60 years of the space age, that is exactly how we treated access to orbit. To understand why, we have to look at the origins of modern rocketry in the strategic arsenals of the Cold War. Early launch vehicles like the Atlas, Titan, and Thor didn't begin as scientific transports. They were repurposed intercontinental ballistic missiles. These systems were engineered to deliver a payload to a target and detonate. Because they were weapons built for highly destructive one-way trips, hardware recovery was never part of the design equation. As a result, the early space program inherited a deeply institutionalized assumption. Spaceflight was a one-way journey, and treating multi-million-dollar precision hardware as disposable trash was simply the cost of doing business. This mindset was locked into place by the cost-plus contracting models used by the government to fund early aerospace development. Under a cost-plus structure, a contractor's profit is directly linked to their total expenditures. Legacy aerospace firms realized larger absolute fees by allowing development timelines to extend and budgets to swell. With the government absorbing the financial risk, contractors faced zero market pressure to optimize their manufacturing or pursue hardware reusability. Even relatively modest expendable launch vehicles maintained an average price tag of $25 to $50 million for a single flight. This expendable model reached its peak with the massive Saturn V rocket. Discarding its enormous booster stages after a single use meant each launch cost the equivalent of $465 million today. As this chart shows, the sheer expense of throwing away the vehicle every time created a persistent financial barrier. It cost up to $40,000 just to deliver a single pound of payload into low Earth orbit. Space exploration was effectively grounded by high-cost contracting models that made orbital access a financial impossibility for all but a few government agencies. In the early 1970s, NASA proposed the Space Shuttle program as the solution to these prohibitive costs. The agency promised a fully reusable system that would operate at a routine cadence of 24 missions per year, driving the cost of space access down to just $1,000 per pound. In practice, the shuttle program fell far short of those targets. Over its 30-year operational life, the system averaged an astronomical $1.5 billion per launch. The intense complexity of refurbishing the orbiter between flights meant that taking mass to orbit still cost roughly $27,000 per pound. Other nations attempted similar programs, most notably the Soviet Union's Buran spaceplane, which launched only once before the program was canceled. Smaller experimental projects tested vertical takeoff and vertical landing, like the McDonnell Douglas DC-X, but they remained suborbital testbeds. Ambitious single-stage-to-orbit designs, like the Lockheed Martin X-33, never progressed past the prototyping phase. After 3 decades of billion-dollar programs and heavy refurbishments, a consensus settled over the aerospace establishment. Building a truly cost-effective, reusable rocket was a financial and engineering dead end. This conclusion was anchored in a specific mathematical constraint known as the mass penalty. Looking at a rocket booster's cross-section, propulsive landing requires heavy legs, guidance hardware, and reserve fuel. Because rockets operate on tight margins, every pound of landing gear means one less pound of paying cargo delivered to orbit. The prevailing calculations suggested that the physics of vertical landing were so unforgiving that a reusable orbital vehicle would be left with virtually zero practical payload capacity. Yet the alternative meant sacrificing the massive first stage, the component that provides the initial thrust and makes up the vast majority of the vehicle's total structure. For legacy contractors and government agencies, the science was settled. The physical laws of orbital mechanics dictated that to reach space, you had to throw your most expensive hardware into the ocean. In the early 2010s, the emerging private space sector began to challenge this deeply entrenched engineering dogma. They publicly pursued what the legacy establishment openly mocked: the vertical takeoff and vertical landing of an orbital-class rocket. The strategy focused entirely on salvaging the rocket's enormous first stage, a single component that accounts for 70 to 80% of the total vehicle cost. Doing so required a vehicle traveling at hypersonic speeds to separate in the upper atmosphere, physically flip its skyscraper-sized structure around, and fly backward through the intense heat of re-entry. It then had to reignite its engines to slow down, aiming for a pinpoint landing target on a surface hundreds of miles away from its launch pad. Despite the insistence of experienced aerospace engineers that the mass penalty made this impossible, the private sector succeeded. Propulsive landings proved that a vehicle could carry landing hardware and still deliver heavy payloads to orbit, breaking a 60-year assumption and proving the traditional establishment mathematically wrong. The immediate consequence of this engineering success was a collapse in launch costs. This graph tracks the effective cost of putting 1 kilogram into low Earth orbit. We see it fall from roughly $54,000 during the Space Shuttle era down to around $2,720 on a reusable Falcon 9. That reduction of more than 90% inverted the economics of the entire commercial space industry. Business models that were completely financially unviable a decade ago are now routine operations. Satellite operators are now building and launching constellations of thousands of spacecraft, a scale of deployment premised entirely on these new launch prices. Looking further ahead, bringing launch costs down by orders of magnitude moves the physical settlement of other planets from science fiction into a logistical reality. Solving the mass penalty physically unlocked the solar system, transitioning space travel from a government monopoly to a scalable commercial industry. We know they managed to land a falling skyscraper on a pinpoint target, but doing so required an entirely new approach to control logic and convex optimization. We'll explore exactly how the onboard math makes that landing possible in the next episode. 2.5 minutes after liftoff, the Falcon 9 reaches main engine cutoff. The first stage booster separates at an altitude of 80 kilometers, traveling at speeds approaching Mach 10. To return to Earth, the booster must immediately reverse its orientation. High-pressure cold gas thrusters fire bursts of compressed nitrogen to rotate 180 degrees. In the vacuum of space, aerodynamic control surfaces like wings or fins have no air to push against. The cold gas system is the only physical mechanism available to manipulate the vehicle's pitch, yaw, and roll. The booster is now a 25-ton, nearly empty cylinder of propellant tanks, hurtling violently away from its intended recovery zone. Surviving the physical stress of stage separation initiates a strict, real-time physics problem. From this moment on, the vehicle must navigate the descent entirely on its own. Before it can safely ignite any engines to change course, the rocket's flight computers must calculate their exact position, velocity, and orientation in three-dimensional space. The system achieves this through sensor fusion. Dual redundant inertial measurement units equipped with fiber optic gyroscopes and accelerometers track the high-speed rotational and translational forces acting on the booster. On this flight computer schematic, GPS data provides a positional baseline. A highly optimized Kalman filter merges these low-frequency updates with high-rate inputs from the IMUs. This data flows into an actor-judge triple-string computing system featuring 3 independent dual-core processors. For every calculation, the processors continuously compare their results. If one string produces an inconsistent answer due to hardware drift or a radiation error, the system ignores it, relying on the strings in agreement. This high-speed, redundant sensory network maintains a continuous state estimate, preventing a massive, high-velocity asset from becoming an uncontrolled hypersonic projectile. Looking at the layout of the 9 Merlin 1D engines, we can see the configuration used for the boost backburn. The outer pair and the center engine ignite to cancel the rocket's forward horizontal velocity and drive it back toward the landing zone. To prevent catastrophic structural shock to the vehicle's frame, the startup sequence is staggered. One engine ignites first, followed milliseconds later by the symmetric outer pair. Following the boost back, the rocket descends to an altitude of 55 kilometers. Here, it plunges into the thickening layers of the atmosphere at hypersonic speeds. The booster initiates a re-entry burn. The supersonic exhaust plume expands forward and outward, creating a physical barrier deflecting the incoming supersonic air. This retropropulsive plasma shield reduces the peak radiative and convective heating on the rocket's fragile aluminum skin by 30%. Without this precise thermal management strategy in place, the intense atmospheric friction would disintegrate the booster before it ever reached the lower troposphere. As the re-entry burn ends and the engine shut down, the booster deploys 4 titanium grid fins to assume aerodynamic steering control. Unlike solid airplane wings, which would experience shockwave separation and stall at transonic speeds, the grid fins' open lattice cells allow airflow to pass directly through. This provides control torque across all descent regimes. An autonomous convex optimization algorithm calculates dozens of landing arcs, discarding flawed paths to find the mathematical ideal. The trajectory is biased toward the ocean, calculating a sharp lateral divert maneuver to the pad at the very end. The flight computer will only command the thrust vector control actuators to execute this final divert if internal telemetry parameters report that the vehicle is completely healthy. If the engines fail to relight or the control loops detect an anomaly, the rocket simply continues its default trajectory. This strict fail-safe philosophy guarantees that a total system failure results in a harmless water splashdown, protecting both ground infrastructure and recovery crews. At roughly 5 kilometers above the surface, the booster enters the terminal landing phase. As the vehicle's velocity drops, the grid fins lose their aerodynamic authority. The Falcon 9 physically cannot hover. The massive propellant tanks are now nearly empty, meaning the thrust-to-weight ratio produced by a single Merlin engine, even at its minimum 40% throttle limit, is significantly greater than 1. The booster executes a maneuver known as the hover slam, or suicide burn. Using real-time distance measurements from radar altimeter pings, the flight computer rapidly adjusts the engine's thrust and hydraulic gimbals. The margin for error here is effectively 0. The deceleration curve must be perfectly tuned so that the rocket's downward velocity reaches exactly 0 meters per second at the precise millisecond its altitude reaches 0. The landing legs deploy in the final moments of descent. The engine cuts off exactly as the vehicle contacts the deck, the physical culmination of thousands of instantaneous autonomous calculations. Once the booster is on the deck, a low-profile, heavy steel-tracked robot named Octograbber drives out of a blast-protected garage. The rocket is extremely top-heavy and exposed to rough ocean swells. Octograbber positions itself underneath the vehicle and uses 4 hydraulic arms to clamp on to the Octoweb structural ring, anchoring it to the drone ship. Catching a first-stage booster from space relies on deterministic math and real-time sensor processing, but transporting this charred, battle-tested hardware back to port to fly again presents an entirely separate engineering challenge. Look at the soot and scorch marks on this Falcon 9 booster standing on the drone ship. It looks exhausted, and for good reason. It just returned from the edge of space. Minutes earlier, this hull was violently vibrating as atmospheric plasma washed over it during re-entry. Inside, its turbopumps were spinning at 36,000 RPM, pushing cryogenic propellants through an inferno. For decades, the aerospace industry accepted a staggering paradox. Engineering marvels built to withstand these exact extremes were intentionally allowed to fall into the ocean and sink after a single flight. Recovering and reusing this surviving hardware transitions the industry toward a model of high-frequency logistical turnaround. This chart compares the historical cost of disposable rockets with the modern reusable model. A traditional launch can cost anywhere from $150 million to $2 billion. By recovering the hardware, the marginal cost of turning around and flying a reused Falcon 9 drops to roughly $15 million. When that tall traditional cost bar vanishes, the savings compound. Every time an existing booster is flown, instead of building a new one from scratch, it generates a financial dividend. You can finance dozens of flights for the price of one disposable rocket. This is exemplified by vehicles like Booster B1067, which has survived 23 distinct orbital missions and safely returned to Earth every single time. To make that math work, the massive, highly complex process of inspecting and repairing an aerospace vehicle had to be compressed into a predictable 9-day industrial pipeline. The clock starts the second the booster touches down. Before crews can even approach, the vehicle executes an autonomous passivation sequence, venting residual reactive propellants and high-pressure gases to eliminate any explosive hazards. Once safed, recovery crews attach heavy steel shoes to the carbon fiber landing legs. The 15-story vehicle is then secured and transported along public roads back to a high-throughput processing facility known as Hangar X. Physical inspections are entirely dictated by flight data. Automated telemetry downloaded from the launch highlights specific thermal gradients and vibration profiles, telling engineers exactly where to look for high-stress wear. From there, non-destructive testing takes over. Laser tracker metrology scans the 70-meter airframe, verifying the intense heat and aerodynamic forces haven't warped the structure by more than 0.02 degrees. By relying on data-driven triage, technicians avoid tearing down the entire rocket by default. Only the components that flag a warning get physical attention, keeping the turnaround time locked into that strict 9-day window. The heaviest physical maintenance happens at the base of the rocket, inside the 9 Merlin engines. This diagram shows a coolant channel experiencing coking. Kerosene soot builds up inside during flight. To prevent blockages, a chemical flush clears the residue. Next, borescopes inspect the turbopump turbine blades, searching for microscopic stress fractures caused by extreme pressures. Finally, crews replace the mandatory physical consumables. Deformed aluminum crush cores are extracted from inside the telescoping landing legs and swapped out, and the highly reactive TETEB fluid, used to ignite the engines, is reloaded. What used to be a delicate, bespoke aerospace engineering task is now treated like rapid, standardized fleet maintenance. This pipeline works. It allows the Falcon 9 fleet to achieve an operational cadence of over 160 flights in a single year. But physical limitations remain built into the architecture. The entire second stage is still discarded to burn up in the atmosphere. On the ground, manually servicing the carbon fiber landing legs and thermal protection shields consumes valuable time and slows down the turnaround clock. While economically successful, this is still partial reusability. It cannot ultimately scale to the rapid, massive, heavy tonnage requirements needed for true interplanetary settlement. Look at the massive scale of the Starship and Super Heavy booster stacked on the launch tower. This vehicle was designed from the ground up to solve those exact bottlenecks and achieve full, rapid reusability. Instead of landing on physical legs, it utilizes the Mechazilla catch concept. The launch tower itself features giant mechanical arms designed to close around and catch the returning booster mid-air. Catching the rocket this way strips away the dead weight. It completely eliminates the need for carbon fiber landing legs, single-use crush cores, and the refurbishment time required to reset them. Down in the engine bay, the next-generation Raptor 3 routes all its fluid and electrical lines internally. This protects the critical components from thermal degradation during re-entry, eliminating the need for fragile, maintenance-heavy external heat shields. By completely eliminating expendable upper stages and vulnerable physical landing hardware on the booster, the marginal cost of launching a massive payload vehicle gets pushed closer to zero. Once launch costs drop that low, orbital logistics shift. The focus moves from placing single satellites into orbit to hauling massive, heavy-tonnage infrastructure on a regular schedule. This economic shift makes it financially viable for humanity to move past temporary outposts. It provides the heavy logistical supply line required to construct permanent bases across this vast, cratered lunar surface. And it secures the supply chain for the ultimate destination, establishing sustainable habitats here on the dusty geological surface of Mars. That entire logistical capability traces its lineage directly back to a single, soot-covered Falcon 9 booster standing on a barge, proving that a rocket could be flown again. Mastering these unglamorous cycles of rocket refurbishment establishes the high-cadence logistical support necessary for a permanent presence in deep space.